So, hey everyone, today I'll be teaching you the intuition behind the Leibniz Integral Rule. You might have seen this form where we have the derivative of an integral uh, of a function of two variables, which is equal to these two terms added along with an integral of the partial derivative of f with respect to x and with respect to t. So, to look at to understand the intuition behind this, we need to look at the geometry, how what the left hand term is, and what the right hand term is. So let's look at the left hand side first. I've got a simulation with me, and I'll tell you the basics in the simulation. See, the blue slice, the slice at x, and the yellow slice represents the slice or the area at x plus d. So now let's look at the LHS first. What does the LHS mean? The LHS looks like this: a of x to b of x dot dt d by dx. What is this integral doing? What this integral actually spits out is a rule of area sweeping along the t-axis for any arbitrary value of x. It basically gives us it basically gives us a rule of the area as a function of x when we substitute the limits. And once we differentiate that rule, we get it tells us how much is the area changing, when we take a step dx. That's what it tells us. How much does the area change when we take a step dx, obviously along the x-axis. Now to visualize this, what we are trying to say here, what the left hand side is trying to say here is this, that if you carefully look at this, see, the blue slice represents the slice at x and the yellow represents the slice at x plus dx, right? So now in x-axis is pointing outwards from the screen, and this is the z-axis and this is the d-axis. Those two are clearly visible, right? So what we are doing here is we are finding how much the area changes, which is the change is this. If you can compare, this is how the area changes, right? From the simulation you can see, if we took a small step, and this is how the area of this slice changed, and how much the area changed on the surface and how much the area changed on the edges. Okay, so what this spits out is actually this change. Simple. Now what the right hand side tells us: the RHS looks like this. We've got an integral of the partial derivative of f with respect to x, that is, and we are integrating with respect to t from a of x to b of x, and we are adding the other two terms. I'll explain. Let me write this first. Yeah. So the other two terms were f x at b of x dB by dx plus f of x a of x dA by dx. Yeah, there was a negative sign here, but I'll tell you how why do we put a negative sign here. Okay, let me write the negative sign there. For now, just let's put a positive sign here. I'll tell you why we put a negative sign here. So let's look at this integral first. What this is doing. So this integral calculates the area of this patch. And how it does that, I'll explain you how it does that. But that integral, which is this, calculates this rate of change. So I'll tell you how we are calculating the rate. So now let's look at what this integral tells us. See, delta f is the infinitesimal small increase in f, that is this height. That is this height, right? Delta f, the small change, a small increment in the height when we take a small step dx. And what this function is doing when we integrate it with respect to t, when we multiply delta f with dt, what we are doing here is we are multiplying this small increment in f when we took a step along the x-axis by a small step dx, and what we are multiplying it is by dt. Let's split. We are sweeping along the t-axis, right? When integrating with respect to t, we are sweeping along the t-axis multiplied by some value. That's what integration means. So let's first split our axis into small dt's. dt, dt. Okay, so for and what we are actually doing is we are summing up this small dt times small changes in f, that is along the z-axis, per unit delta x. This is what this actually means. So this is the area. This represents the area of this tiny patch. This represents the area of this tiny patch. This represents the area of this tiny patch. And what we are doing, what this integral is doing, is we are adding up this entire patches so we are adding up this entire patches from boundary ax to bx. This represents the boundary along the t-axis. So we are adding this integral. What is this integral is doing is this is adding this patches, and it gives us how much this patches change along with how much this patches change when we take a small step along the x-axis. This is what this integral means. So now we need to account for the now we need to account for the edges as well, the area of the edges, right? Because we ultimately want the LHS to be equal to the RHS, right? So the area of this part and this part is what we need to find out. For that, let's get back to our 3D simulation. See, we need how much did the area change? How much did the boundary of T, which the boundaries are defined by A of x and B of x, right? How much the boundaries of T changed when we took this step in along x? This gives us the width. This gives us the width of the this patch, right? How much did the boundary of T changed when we took a small step along the x-axis? And the length of the small step was dx. That gives us the width of this patch, right? Which is dB. If we consider this as b, which is then this should be dB, right? And when we took a this is the rate of change in boundary when we took a small step dx, right? And what was the height of the function? It was simply the and what is the height of this patch? It is simply the value of b. It is simply the value of the function at b, right? So we get this for the area. The rate of change in area is the change in area by small step size dx. And what was the change in area? The height of the function, which is f of x. F of x at, I'll call this with the bound at b of x multiplied by small change in b. That accounts for the area of the edge. Similarly, we have the area of this edge, which is f of x at a of x multiplied by db dA by dx. Yeah, that simply means f of x ax dot dA by dx. Now I'll tell you why are we so once we add all these three, we arrive to this equation. We arrive to this RHS. That is the area of the patch at the surface and the edges. These are two terms account for the edges, and this term account for the surface. And these are giving us the rate of change when we are. This gives us the rate of change. This gives us the rate of change, or rather change in area at the surface, or change in area between these slices at the surface per dx. And these two terms are giving the change in area at the edges per dx. So that's how the LHS is equal to the RHS. To summarize, the LHS was telling us, the LHS asks us to first evaluate the integral for any arbitrary value of x, for any while sweeping along / summing along the t-axis. And then we simply differentiate that, and it spits out a rule, and we simply differentiate that rule, and it tells us how much the area changes when we take a small step dx. And what the RHS tells us, the three terms in the RHS tell us that the integral term tells us, the integral term, which I'll write a of x and b of x del f by del x dot dt. This tells us the area change between the slices when we took a step slices per unit dx. Okay, that gave us the tiny strip of area, and now we need the area of the edges. Right, so the area of these edges was given by those boundary terms. Okay, so now the final piece that remains is the negative sign here, right? Why are we having a negative sign here? That is simply due to the directionality of the increment, right? The direction of the increment dt, if we consider this direction to be the positive increment, then this should be considered as negative dt, right? So just while adding the area, we consider the sign, and we have a negative sign here. Okay, so if you really understood the intuition behind the Leibniz integral rule, do not forget to like this video. Thank you.